So this, in fact, is basically the solution of the problem. And let's just talk for a few minutes about what it's used for. So this is basically the technique that is exactly used for magnetic resonance imaging. So MRIs, if you have to say one of the interesting applications of quantum mechanics to technology, MRIs, magnetic resonance imaging, is one of the great ones. So how does it work? Well, it's a very useful device. In fact, it revolutionized medicine because it goes much beyond what you can do with X-rays. It's very popular. I imagine a good fraction of you have had an MRI. Let's see, how many people have had an MRI in their lives? Yeah, we're pretty much, I think, 60% of people here. So you remember getting into this cavity. Well, you've experienced there a large, if you worry about cell phones or radiation, well, there you were with 2 Tesla, 20,000 Gauss, a big, big magnet. It's big enough that it has to be done cooled with liquid helium at 3 degrees Kelvin. So you can get the currents big enough and the magnetic field big enough. So they put you into this cylinder, a solenoid, and there you go. And it's not dangerous unless you have you forget some metal or some device like that. In fact, it says in WebMD that if you have some sort of tattoos, if they used iron ink, it can burn your skin, or you could have some problems. Anyway, if you're claustrophobic, they have MRIs that are open air, but they're less powerful, less strong magnetic field. So this is 2 Tesla, roughly. And so what happens is that basically this thing just is trying to figure out the local concentration of water. It begins like that. The magnetic fields react with the hydrogen atoms, in fact with the protons inside there. Each proton has a magnetic dipole moment. It gets roughly aligned to the magnetic field, to this B naught. So the protons get aligned to the B naught that is going in here, B naught. So the proton spin is up there. In fact, not because of temperature effect, not all of your protons in your body get aligned. Maybe 1 in a million does, but that's high enough. And then they send this 90-degree pulse. So this thing starts spiraling, and then it finally goes into this direction, and it rotates like crazy. Then, as it rotates like crazy, a rotating dipole moment is like a generator of electromagnetic waves. So it generates an electromagnetic wave, and there are detectors all over, that pick up this signal. The strength of that signal is proportional to the concentration of water. So it gives you an idea not to distinguish like solid matter versus soft matter, but all kinds of liquids. So it's very, very useful. So you pick a signal over here, and you get it from a receiver, and it tells you about the local concentration of water. And therefore, it allows you to distinguish different tissues. Some tissues have lots of water, some tissues have less water, so it begins to distinguish different tissues. Now, there's 2 more things that people do. This spin is rotating very fast, but there's a relaxation time. After it rotates for a while, there's a time T2 is relaxation of this rotation, relaxation time. And then there's another time, T1, which is the time after this is turned off, that it takes the spin to go back and go back again to the original position. So 2 times. The relaxation time in which you sort of lose your rotation here because it's interacting with other spins. It's called spin-spin relaxation. And then an interaction with the whole set of neighboring atoms that brings it eventually back up and aligns it to the magnetic field. So you measure 2 things, T1 and T2. And those are like very good clues because you can put any liquid in the machine and measure its T1 and T2. And then you produce a table of T1s and T2s. And then if you want to figure out what kind of thing you have in your body, they look it up, and immediately they may know what are the possible candidates. In fact, T2 is actually enough to distinguish white matter, gray matter, and fluids in your brain. Totally different T2s. T1s, helpful to discuss all kinds of things as well. So basically, people have figured out how to do that. Finally, one last thing. When you go into the machine, it sometimes makes noises, pop, 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 big noises. And those are gradient magnets that are being moved. You see, basically, if this thing would be like that, you would pick up a signal and you wouldn't know where it comes from. So what these people do now, this has gotten extremely sophisticated. They put a gradient magnet which changes the value of B naught locally by increasing it. For example, the B naught is not really constant in Z, but it changes. So the omega naught of rotation of the spins changes as well. So with a sufficiently high gradient of magnetic field, they can have spatial resolution. If they pick a signal a little bit higher frequency, they know it's a little bit higher up in your body. So they get resolutions with these magnets of about, how much? Very high resolutions, 0.5 millimeter. At the end of the day, it's a great machine and lots of mathematics in reconstructing images, lots of computation, lots of experimental analysis of constants, much of it phenomenological. It would be hard to predict those constants, but you can measure them. So it's very, very practical and very nice. So it's a nice application, and we'll leave it at that. Are there any questions? Not that I know much more about that. But it's a junior lab experiment as well. So at least the calculation is fairly straightforward, and the technology is just amazing.